So hello everyone. Today's our discussion topic is on sulfur-containing amino acid metabolism. So we'll have a revision on sulfur-containing amino acid metabolism. So far, university has been asked two questions from this session. Question number one: define transmethylation. Discuss the synthesis, functions, and catabolism of amino acids involved in transmethylation reactions and disorders associated with its metabolism, which has come as an essay. It carries 10 marks. And the second question from this topic, transmethylation reactions with 4 examples of important products formed, which carries 5 marks. So there are 3 sulfur-containing amino acids: methionine, cystine, cystine and cystine. These 3 are the sulfur-containing amino acids. Among this, the methionine is an essential amino acid, whereas cystine and cystine are non-essential amino acid. So from methionine, these cystine and cystine can be synthesized along with the help of other non-essential amino acid serine. So the methionine will be catabolized or metabolized by two mechanisms: transfer of methyl group of methionine by transmethylation reaction. Second, the conversion of demethylated portion of the methionine, that is S-adenosine homocysteine, to cystine and cystine. The definition for transmethylation is transfer of methyl group from methionine to an acceptor molecule, and this process is known as transmethylation. So the methyl group of methionine becomes available for transmethylation only in an active form, that is actually S-adenosyl methionine. So the synthesis of S-adenosyl methionine done with the help of two things. One is the enzyme methionine adenosyl transferase with the hydrolysis of ATP molecule. So the adenosyl group from the ATP will be transferred to the methionine, and the active methionine or S-adenosyl methionine synthesis occurs. So here the methyl group of active methionine SAM is very active and can be enzymatically transferred in synthesis of multiple compounds. So there are so many examples for the transmethylation reaction. This is the general reaction of transmethylation reaction. SAM will donate its methyl group to the acceptor and itself become a methylated product, and SAM will be converted into S-adenosyl homocysteine, that is SAH. So these are the examples of transmethylation reaction. So many examples have been given. Guanidoacetate to creatinine. So wherever it is, you are supposed to write it as an equation or reaction. In that you can write SAM to SAH. Guanidoacetate accepts it, methyl group itself will be converted into creatinine. So no epinephrine to epinephrine, epinephrine to metaepinephrine, ethanolamine to choline, so on. So all these are the examples for transmethylation reaction. Now the significance of transmethylation: so many compounds become functionally active after methylation. And protein methylation, specifically the amino acid residues methylation, helps to control the protein turnover, and methylation protects the protein from immediate degradation, that we are learning in transcription, translation, etc., post-transcription and post-translational modification. And in plants, SAM, that is acetylmethionine methionine, is a precursor for the synthesis of plant hormone ethylene. So this is all about transmethylation. So if the question comes as transmethylation for 5 mark with the example, you are supposed to write these many points. Now the second part, which explains the metabolism of sulfur-containing amino acid, or what happens with this demethylated portion of methionine, that is S-adenosyl homocysteine. The fate of this S-adenosyl homocysteine is that it will finally converted into cystine and cystine. So this much portion we have already been explained along with the transmethylation reaction. Now the second part, what will happen? This S-adenosyl homocysteine, what will happen? Hydrolytic cleavage of this SAH occurs with the concomitant production of homocysteine and adenosine. Hydrolytic cleavage, that means a water molecule inserted, and with the enzyme here it is adenosyl homocysteinase, and the products are homocysteine and adenosine. And this homocysteine has another fate that which will be utilized for the resynthesis of methionine, that will be explained later. Now the next part is that homocysteine then condenses with another amino acid, that is serine molecule, to form cystathionin with the help of enzyme cystathionin beta synthase enzyme. Further, what will happen? Hydrolytic cleavage of cystathionin leads to the formation of homoserine plus cystine by the enzyme cystathionin lyase, cystine and homoserine. And what will happen? And this requires a coenzyme pyridoxal phosphate. Clear? Now the cystine may be oxidized to cystine. You can see cystine will be oxidized to cystine, or homoserine, which undergoing a deamination reaction by homoserine deaminase to form alpha ketobutyrate. Then alpha ketobutyrate undergoing oxidative decarboxylation to form propionate coenzyme, which is catabolized by through the methylmalonyl coenzyme to succinyl coenzyme, and finally which will be entering into TCA cycle. This is the overall fate of methionine. So we have seen that transmethylation reaction we have seen. Then from demethylated methionine, how the another two sulfur containing amino acids cystine and cystine synthesized will be also explained. Now the another part is that we have to explain the metabolism of these cystine and cystine. So in previously we have seen the synthesis of cystine and cystine from methionine. Now we have to discuss in detail about the metabolism or catabolism of these cystine. So the cystine, which is a nutritionally non-essential glucogenic amino acid, and it is synthesized from two amino acids. We have seen that methionine and serine molecule. Okay, now in that pathway itself we have seen that cystine undergoing reduction to form cystine, which is a reversible reaction. Here also which will happen, the major catabolic fate of cystine is conversion of cystine to cystine, and the reaction is catalyzed by the cystine reductase enzyme in previous figure which was shown. Now the catabolism of cystine occurs, or cystine can be catabolized by two route by first one is transamination reaction, second one direct oxidative pathway. So the transamination pathway, you can see there, this is the first pathway, transamination pathway. Cystine undergoing transamination with the help of cystine transaminase enzyme, and the amino group will be accepted by alpha ketoglutarate, and itself will be converted into as a new amino acid as glutamic acid and new keto acid as beta mercaptopyruvate. And this beta mercaptopyruvate then undergoes desulfuration by enzyme sulfur transferase enzyme to form the keto sugar as pyruvate, keto substance as pyruvate, and the sulfur is eliminated in the form of hydrogen sulfide. This hydrogen sulfide is reduced by, along with the help of reduced glutathione, which will be reduced or converted into sulfide, then immediately it converted into sulfide and then to sulfate. And this sulfate formed by in this manner can be excreted in urine or converted into active sulfate, that is PAPS. PAPS is phosphoadenosine phosphosulfate by using ATP. And PAPS, which is a source of sulfur in the synthesis of other biomolecules like glycolipids, sulfolipids, etc. And or either in the form of sulfate itself can be excreted through the urine, or it will be converted as phosphoadenosine phosphosulfate or active sulfate molecule. That is the transamination pathway. And the second pathway is that this is direct oxidative pathway. Here the cystine is oxidized to cystine sulfinate. You can see cystine is oxidized to cystine sulfinate with the help of enzyme cystine dioxygenase, then which will be decarboxylated to hypotaurine, which further oxidized to taurine. That is one fate. Or else what can happen? This cystine sulfinate can conjugate. Cystine sulfinate may undergo transamination and give rise to sulfate. Finally, sulfate and sulfate can be converted into active sulfate. So this is overall fate of cystine through the transamination pathway and direct oxidation pathway. Now the major metabolic functions of cystine is that it leads to the formation of glutathione and has some role in amino acid transport through Meester cycle, then coenzyme role, then RBC membrane integrity with the formation of glutathione and met hemoglobin synthesis, conjugation for detoxification, activation of enzyme, formation of taurine, keeping the correct structure of protein. All these are the functions of cystine. Now, the inborn errors associated with the sulfur-containing amino acids are cystinuria, cystinemia, and homocystinuria. So, the cystinuria is actually occurs due to defect in renal reabsorptive mechanism for 4 amino acid, that is cysteine, ornithine, arginine, and lysine. Short form you can write as COL. C for cysteine, O for ornithine, A for arginine, and L for lysine. So, the defect in renal reabsorption of these 4 amino acids, which leads to a specific condition that is known as cystinuria, where there will be excretion of all these amino acid occurs. Excretion of cysteine up to 30 times occurs. Then this cysteine, it forms an insoluble crystals in the urinary tract and it leads to the formation of renal calculi, and it leads to cystinuria, which is usually a benign anomaly. Then cystinosis. Cystinosis, a cystine storage disease where there will be accumulation of cystine occurs in fluids. So it is a rare lysosomal disorder. Here the defect is that defective carrier mediated transport system of cystine. Cystine crystals are deposited in tissues and organs, specifically the reticuloendothelial system, and it leads to specifically generalized aminoaciduria, and renal function will be getting impaired. Patient may die young from acute renal failure, that is cystinosis. And now the most important inborn error of metabolism associated with the sulfur-containing amino acid is homocystinuria. It is the disorder of methionine metabolism with high blood and urine levels of homocysteine and methionine. There are multiple types of homocystinuria, but the major one is due to the deficiency of cystathionine beta synthase enzyme. So where there will be accumulation of homocysteine in blood occurs. Symptoms of homocystinuria are usually the patient may develop mental retardation and a specific gait that is known as Charlie Chaplin gait due to skeletal deformities. In eyes, it may lead to ectopia lendis, that is subluxation of lens, myopia and glaucoma. And homocysteine causes activation of Hackman's factor, so that may be the reason for myocardial infarction. This may lead to impaired platelet adhesiveness and life-threatening intravascular thrombosis. The diagnosis for homocystinuria: cyanide nitroprusside test will be positive in urine. Urinary excretion of homocysteine will be more than 300 mg per deciliter, mg per 24 hours. Plasma homocysteine and methionine levels are increased. Treatment: the patient should take diet with low methionine and rich in cysteine. Sometimes the other reason, the affinity of apoenzyme to the coenzymes is reduced. That is why it is mandatory to supply with the pyridoxal phosphate. The coenzyme given in large quantities will correct the defect. Thank you. This is all about the answers for 2 questions. First one, the sulfur-containing amino acid metabolism overall for the 10 mark and transmethylation reactions. Thank you.